Today we want to talk about periodic motion, and it is any motion that is caused by a restoring force, and then it has that oscillation where it's that repetitive motion. So for instance, if I'm looking at a spring, then I might say I have the spring anchored against a wall here, and there's a mass against it that I either push into the wall or I stretch the spring out like that, and it causes the spring to oscillate, or that mass to oscillate back and forth between those. Remember that the force that is causing it to want to be restored, that restoring force, is going to be the force that we studied earlier, that's Hooke's law, the kx, and we will call it negative because it's a different perspective, that it's the spring trying to restore itself, not us pulling against the spring. So whenever we look at Newton's second law, F equals ma, we can substitute that in that negative kx for the force, and then remember that the acceleration is the second derivative of the position. So we'll have the d2x dt squared, and then what we can look at that is if I reshuffle this around, I end up with this equation that says the second derivative is equal to negative this k over m, so I divide my m to the other side, times the x function. So it's interesting, some things that I note there is, first off, the second derivative of the position gives us some coefficient times the position again. So kind of keep that in the back of your head, because that's going to play an important role later on. Now, if we look at another one, we might say, hey, a pendulum. So I have this pendulum here that is oscillating. There's something hanging on the bottom. There's a certain length here. Remember that there is a force of gravity pulling down on the pendulum, and the pendulum is going to swing back and forth across a line that looks like that. Now, what is the restoring force here? Isn't it the force that's pulling the pendulum that way, or that diagonal value of the gravity? And so if this is the force of gravity, then this force is going to be the Fg gravity perpendicular, which would be mg, and it would be sine theta. So mg sine theta. So whenever I go to do F equals ma, then I can say, again, negative, because it's restoring itself. So it's your frame of reference there. So negative mg sine theta is equal to md, second derivative of the acceleration. Notice that I have an s there because it's position. It's not particularly the x position, but what it really is this arc length that it's traveling over. And if you remember from your math class, the arc length is really the length of the pendulum times the angle that it is traveling through. And so we're going to take the second derivative of that arc length. Now I can substitute that L theta in here. L is a constant because it's not changing. It's the radius, or the length of the pendulum there. So if I pull the L out, then I get the second derivative of the position with respect to time is equal to negative g over L, because I'm dividing the L over, times the sine of theta. Now, an interesting thing here is when we talk about that sine of theta at very small angles of theta, then the sine value is really the theta value. So I can simplify that kind of in a way at the beginning of the year. You say, well, let's just get rid of friction and ignore it for now, because it doesn't play that crucial of a role unless I want to get super detailed. The same thing here. I can sort of simplify that sine theta value and make it be the theta value. So now notice again that the second derivative of that angle gives us a coefficient times the angle itself again. Kind of a pattern that we're developing here. Now, a physical pendulum. So a physical pendulum would be like if I had a rod, maybe I take a meter stick, I drill a hole at the top here, and I have it swing off of that anchor at the top. Remember that the center of mass is going to be at the center of the meter stick if I'm doing a uniform linear bar there. Uniform linear bar. And I might say that center of mass, that there is a distance of d here from the pivot point to the center of mass. So again, similar to what we had over here with the regular pendulum, I would say that the restoring force that's pulling this way is going to be that mg sine theta, and I put a negative in front of that because it is the pendulum itself is that force. So now if I'm looking at a physical pendulum, I'm probably not going to be dealing with F equals ma. I'm probably going to be dealing with angular motion and say, hey, I have to have this torque equals I alpha instead. So again, I have right here the restoring force. Now, remember that torque is going to be a force times a distance, right? Or force times a radius. So that force times the radius, which is our d value, and then I, and then alpha is going to be the second derivative of the angular displacement, or that theta value. So if I simplify that, I can divide I to the other side. I can say the sine of theta is roughly theta, and I can move this over, and then we end up with, again, a very similar equation that says the second derivative of the angular position equals a negative coefficient times the angular position. Okay, moving on. So fourth example that we're going to look at here is a torsion pendulum. Now, we haven't really covered these. I'm just doing this for the heck of it. So we have a circular, maybe there's a disc at the bottom of a string of metal here. And what we're going to do is we're going to twist this torsion pendulum, twist it this way so that what it will do is it will rotate back and forth like that. Because of the tension that's in that metal string or metal wire or whatever it is that's holding the disc up there. So what we would end up with, now you don't necessarily know this value, I'm just giving it to you, that the torque is going to be negative K, which is some, you could think of it as like, you remember how we had a spring constant? So every spring has its own constant that tells you how stretchy or loose it is. Well, the same thing here, every wire is going to have its own constant that tells you how well it will twist, how well it will not twist. And then theta is going to be the angle that we're going to twist that over. So that's going to be that angle. And then we can say I and the second derivative of the theta value. And again, we end up with an equation that looks similar to that. Now, I want to kind of circle the wagons here and go back to an idea that we had way a while ago. And that's just to refresh your memory that remember that the period is equal to 1 over the frequency. And then angular frequency is 2 pi times the linear frequency. Okay, now you might say, well, look, well, who really cares? But if I combine these two, I get 2 pi 1 over omega. And that should start looking familiar to you, especially since we just derived the period of a pendulum and got an equation for that. So if you look at the pattern, look at each of those coefficients. This is a different pattern we're looking at. What are their units in? So for instance, an easy one might be to take this pendulum one and say G over F. Hey, G is gravity, so it's going to be meters per second squared. And if I divide that by a length, which is in meters, then don't I get 1 over second squared? Sort of interesting. Same thing if I take K over M. Well, remember, K is going to be newtons per meter. So I can say newtons per meter. Well, remember, newtons are kilogram meters per second squared divided by meters. And if I divide that by another kilogram divided by kilograms, my meters cancel out, my kilograms cancel out, and I'm left with that 1 over second squared. Hey, I bet if you do the same thing for the physical pendulum and for the torsion pendulum, that they're each going to come out to be that 1 over second squareds also, which means that that coefficient either has to be the frequency squared, right? Or it has to be the angular frequency squared. And if you think through like this period, 2 pi over omega, then let's go with that one because it fits the period of a pendulum that we derived earlier. So I can take and say, hey, the second derivative of the position is equal to the negative omega squared times the position again. And that's what each of these functions at the bottom, that's sort of the pattern that each of them are following. So if I say that omega squared is this K over M, then can't I say the period of an oscillating spring is going to be 2 pi square root of, and remember that's flip-flopped and square rooted, the mass over the spring constant, which is what we studied in the fall whenever we did springs and we talked about energy, right? Now, if we do the pendulum, we just derived this equation. We finished that whole lab where you decided what affects the period of the pendulum. And we said only the length and the gravity. We came up with this beautiful graph that had a really nice, I don't know which way it is for your perspective, a nice direct and linear relationship that we got this 2 pi from. And then the same thing, we can play with these last two, the physical pendulum and the torsion pendulums. Okay, and so that's where we would start looking at what are these functions, how does this repetitive motion, like what's a theme running through this periodic motion, and that would be this one, this omega value and the period of those, and then each of these different equations. Okay, now for another example, orbits. Now the interesting thing about this one is there are 3 different ways that we can go about deriving those equations. So if you think through, we had all of these different ones at the bottom here, and then we found the second derivative of the position, gave us some function time or coefficient times the position itself, and then we have this the period that we can calculate based off of the angular frequency. So if I have an orbit, so maybe this is the Earth rotating around the sun, the first way I can do this is I can do, if you remember gravity, we have gmm over r squared. The two masses will cancel out. Our acceleration is that v squared over r. Then remember that our velocity is also 2 pi r over t, and we can substitute that in, square it. It would get rid of an r here, get rid of an r here, multiply this r over, and we get this r cubed, get our t over to the other side. And when I solve it, notice I end up with that same period equation that is 2 pi square root of some function or some coefficient there. And then we can say from that our omega squared value has to be the reciprocal of that and the not square root value, so the gm over r cubed. Now, the second way we can look at that then is we can also do the same thing where we say gmm over r squared, m times the second derivative of that radius. And then if we get rid of our two m's there, then we can look at this value and say, hey, if I multiply by r over r, then doesn't that give me that same function that is the second derivative times the negative coefficient times the position? And that's where we can also say then that omega squared, based off of the themes that we had or the patterns we had earlier, gives us that gm over r cubed. Now, the third way that we can do this is kind of an interesting mathematical proof. So if we look at this and we say, hey, there's this r value here, and remember that our theta is going to be omega times the time. So we can say that the x value is r cosine theta, the y value is r sine theta, and then that theta has to be omega t. So if I start by saying that my r is going to be the x plus the y value, so r cosine theta, r sine theta, and then I say, well, the first derivative of that is going to be, remember you take the derivative of the inside value here, and you get negative r omega sine, and then you take the derivative of the inside value, so you have the omega, and then you end up with that value. So then if we take the second derivative of that, we end up with this again, where we take the derivative of this, so we get omega squared, and then you flop the value of the sine to cosine, and then you flop the value of the cosine to the sine, and the omega squared comes out there, and we end up with this acceleration equation that looks like that. Now, remember that to get rid of our unit vectors, we can just do the Pythagorean theorem. So we can take and say the square root of the x value squared plus the y value squared is going to give us our a value. And interestingly enough, if I simplify that, can't I pull out, first off, these negatives will square to become positive. Secondly, our r omega squareds are in both terms, so can't I pull those out, which means I'm left with the cosine squared plus the sine squared, and isn't that an identity that is equal to 1? And so we end up with this value that is just the square root of r omega squared, which gives us the plus or minus value of r omega squared. Now, where am I going with that? Is I can take that into this equation that we have, the gmm over r squared, where again, my m's will cancel out. But when I look at this second derivative of the position, isn't that going to be equal to, and I'm going to say it's the negative value just so that my two negatives go away, and I divide both sides by r, and I end up with that gm over r cubed value that is the same thing. Now, there's one more thing that I want to kind of pull your eye to on this one, and that is, let me just make sure I'm on the right track here. So that is going to be, hey, isn't this omega value going to be r v squared over r, like that, which means that's the same as saying r v squared over r squared, so my two r's will cancel out. And isn't that interesting that that's my proof? Remember way back when we studied circular motion, I said, hey, for now you're just going to memorize this, but later we'll prove it. That's the proof that shows that the centripetal acceleration is that v squared over r value. Boom! Okay, moving on. So let's go back to the idea that, hey, remember we were talking about this interesting pattern that we had here, that the second derivative of the position is equal to the negative coefficient times the position again. Well, what kind of function do we have where we have the second derivative of the function is equal to the function again, only negative? and that's got to be a sine or a cosine function. So we end up with, this is the general equation for a wave function for what we're studying. We would say the position is our x value, the amplitude is the coefficient in the front, cosine of some angle. Now notice that we have the omega t is going to be our angular frequency. Omega t is going to be the theta value, or if I simplify that, the omega will be the angular frequency and the t will be the time. And then I'm going to tack on this one that we will sometimes use, sometimes not, and it's called phase. So when we talk about amplitude and looking at this function, wouldn't we say that that cosine value, it's going to oscillate between -1 and 1, which means that when we times it by the amplitude, that our position is going to oscillate between -a and +a. So that's going to be our position function value. When I look at WT then, right here, what are our units going to be in? If I'm talking angular frequency, then our units are going to have to be in radians. So whenever we're dealing with the wave function, our angle is going to be in radians. Then just to kind of explain phase is this idea of if we shift the wave off of what the wave normally is. So for instance, if I have the original wave as the solid line here, and then I shift the wave a pi/2 phase, then I'm going to be shifting it roughly 90 degrees, if that makes sense. If I were to shift it all the way over to this point here, then it would be shifted by a phase of pi. This point here would be 3pi/2, and if I shift it here, then it would be a 2pi. So you get the image that it's just shifting the wave further over, so it's in or out of phase with whatever the normal wave function is. Now, like I said, a lot of times we won't use that, and you will only see this as a cosine omega t, but occasionally you will have that phase function in there, and you just have to know that all it's doing is moving the wave over. So some things we need to talk about then. If this is dealing with the derivatives, then we have to talk about the definition of the derivative, which I did earlier, but I didn't really explain it. So here's the explanation. Remember that the derivative of the cosine of theta with respect to theta is the negative sine theta, and the derivative of the sine theta with respect to theta is the cosine theta. Okay, and that's how if I were to take the derivative of the cosine of theta, I'll get the negative sine, and then when I take the derivative of the sine theta, I'll end up with the, if I take the derivative of this guy, I'll end up with the negative cosine theta, so I'm back to where I started from, and that's kind of the key idea between that pattern we were looking at earlier. Now, one more thing, if you notice up here, we have this omega t is in the theta function, so we need to talk chain rule here. If I'm taking the derivative of this sine of some angle with a coefficient, then in essence, I'm doing a UDU where I'm taking the a theta and saying it's equal to u, and I'm taking the derivative of it, and that's what goes in the front. So if I have the derivative of the sine of a theta, I'm going to end up with the derivative of the angle, which will be a, and then I'm going to have the cosine derivative of the sine, which is the cosine of the original angle. Okay, and that's how you would do these guys that have a coefficient inside the angle value. So if I have this x as a cosine omega t plus phi, then when I take the first derivative of that with respect to time, remember that I'm going to take the derivative of this angle inside with respect to time here, and so I'm going to derive that. This is a constant, it goes away. This is a 1, so it's going to be 1 times that, and then it goes away, and I'm left with that omega value that gets multiplied to the front. Okay, so the omega goes in the front. Then I'm going to take the derivative of the cosine, and if you remember over here on the left, it's the negative sine, so there's my negative sine, and I'm going to have my original angle there. Again, if I take the derivative of that with respect to time again, so the derivative of the velocity with respect to time, then again, I'm going to take the derivative of everything in the parentheses, which will be omega, multiply that times the front, which will give me omega squared. The derivative of the sine, which I wrote wrong here, is not the sine. This is going to be the cosine, and it is not going to have a negative. So I keep the negative that I have there, and then I'm going to keep my original angle there. And so that's how I end up with a function that is the second derivative of the position is equal to the original function with some coefficient in the front. Isn't that awesome? Okay. Let's talk total energy. I'm going to specifically look at a spring, but this applies to all of them. So if I have the total energy as the potential energy plus the kinetic energy, then can I say the potential is 1/2 kx squared and the kinetic is 1/2 mv squared? And I have an x function here that I can plug in for x, and I have a v function here that I can plug in for v, and that's what this next line is. So I have a cosine squared, a squared cosine squared of everything inside there, and I have the omega squared. I just got rid of the negative because it's going to square out. A squared sine squared of everything inside there. Now, remember back when, didn't we say for a spring that omega squared value is k over m? So I can substitute in k over m for that. Since it's squared, I don't have a squared value here, which means that my two m's will go away. And hey, look at that. Don't I have a 1/2 ka squared in front of both of those? I can pull those out and say the cosine squared plus the sine squared. And guess what? There's that same identity that is equal to 1. So all of this goes away and is equal to 1. And I'm left with the total energy is 1/2 ka squared, which would be the spring constant times however the amplitude is that I pull it back at that, whatever that moment is. And that would be the total energy that we would say is for spring. Now, it'd be slightly different, but it would still follow that same pattern if I'm dealing with other things like maybe a pendulum or the physical pendulum or the torsion pendulum. But that gives you sort of an idea of where that total energy comes from. Lastly, let's talk through a sample problem. So a piston in an engine oscillates so that its position varies according to the expression x equals 5 cosine 2t plus pi over 6. So where x is in centimeters and t is in seconds, then we want to, at time 0, find what the position is, the velocity, the acceleration. Well, those become super kind of easy. So for part A, for the position, can't I just say x is equal to 5 times the cosine of 0 plus pi over 6? And whenever we do that, we should end up with a value that is going to be 4.33 centimeters. Okay, now part B becomes a little more interesting because don't we need to take the derivative of that in order to find the velocity? So I can say that the derivative of that is going to be the derivative of the inside of the parentheses. So 2 times 5, my velocity will be 10. Now I'm going to take the derivative of the cosine, which remember is the negative sign. So I'm going to put a negative in front, put my sign there, and times my original angle that goes with that. So negative 10 sine 2t plus pi over 6. Now, if I plug in my 0 for that, so if I plug in 0 for that, then the 2t goes away, and I can just calculate that, and I end up with a velocity that is negative 5 centimeters per second. Now, C, for the acceleration, we're going to do the same thing again. Take the derivative of this inside, which will be 2, times the outside, which will be in negative 20. The derivative of the sine is the cosine value, and then times the 2t plus pi over 6 that goes on the inside. Again, I can put in 0 for the t and solve for what that value is, and I should end up with a negative 17.3 centimeters per second squared for the value of the velocity. Okay, now if I want to find the period, can't I look at that and say, hey, didn't we say that this coefficient here, the 2, is equal to omega, right? And omega is equal to 2 pi times the frequency. So the frequency is equal to 1 over the period. So I'm just doing a whole lot of conceptual jumbling here. And then this is equal to 2. So 2 pi 1 over t, the 2's will cancel out, multiply both sides to get that over, and then can't I say that the period is going to be equal to pi seconds from that. Part E is going to be super easy. We can look at that and say, I don't know, hey, didn't we define this to be the amplitude? So the amplitude is going to have to be equal to 5 centimeters. Oh boy, that was really hard. Number F, if I want to find the maximum velocity, so V max, then aren't I going to want to look at it where I have the cosine is going to be equal to 1 or negative 1, right? Which means that isn't my V max going to be this negative 10 value? Again, boy, that wasn't that difficult. And if I want to find the time that I was at V max, then can I plug that back into the velocity equation, say negative 10 equals negative 20 times the, whoops, up here, this should be acceleration, right? This should be acceleration. A little bit of mistake there. So this is going to be 2 to negative 10 times the sine of 2t plus pi over 6. So those cancel out, and I can say that when is the sine going to equal to 1? Sine of all of that, 2t plus pi over 6. And from there, I can solve for t and end up with a t value that is 1 over 6 pi, which is the same as 0.524 seconds. So again, solve that. You'll take the inverse sine of 1, then you'll subtract negative pi over 6, then you'll divide by 2, and you should end up with that value there, which gives you the period that it would take for that. And that is an example of that. So in summary, remember that we have these different scenarios that we can derive an equation that follows a certain pattern that says that the second derivative of the position is going to equal the negative coefficient times the position itself again. And what that does is it helps us to define this equation or this pattern to be a sine and a cosine function, because of the fact that when you take that second derivative, you end up back with the same function and with a negative value. We also then, if you remember, we have this pi, 2 pi 1 over omega is going to give us our period, which means that each of these coefficients has to end up being the omega squared value, and that's how we can derive each of the period functions. To find the total energy, you're going to take the total potential plus the total kinetic, and that gives you the total energy. And then just as a reminder that the derivative of the cosine of theta with respect to theta is the negative sine theta. The derivative of the sine of theta with respect to theta is the cosine of theta. And that, in a nutshell, is periodic motion.